Hello friends, we were discussing about the mechanical condition or describing the mechanical condition experienced by an area of interest in 2 dimension and in 3 dimension. In 2 dimension, we saw that when your area of interest is inclined or the region of your interest is inclined, then your the mechanical condition experienced by that region comprises of 2 components. So these components include a normal stress, which is given by this expression, and a shear component or a shear stress, which is given by this expression. So even though we arrived at this, or rather we derived this expression in the context of an inclined area of our interest, we saw that this is rather a generalized set of expressions which can be used to describe the mechanical condition experienced by any region. If your region is parallel, then accordingly your theta would change. If your region is perpendicular to the loading direction, then accordingly your theta would change, and you can arrive at any mechanical condition any region experiences by appropriately using the theta values. Now, based on these results, what we did was we considered a 3-dimensional setup and we considered an uni-axial tensile loading. A critical point that we need to remember is these stress conditions, or rather these mechanical condition, they pertain to, or they exclusively pertain to uni-axial tensile loading. So only when your 2-dimensional setup experiences a uni-axial tensile loading, these component of stresses are being experienced by a region of our interest. Now when we have a similar loading condition, meaning a uni-axial tensile loading is acting on a 3-dimensional setup, based on this expression which we derived for 2-dimensional condition, we saw that there are 3 components of stresses a region of our interest experiences. So these components of stresses for an uni-axial loading condition, and for a reference frame something like this, z, x and y axis, for a reference frame something like this, we saw that the 3 components of stresses experienced by a region within a 3-dimensional setup experiencing a uni-axial tensile loading is expressed as this: sigma z P by A cos theta, tau zx P by A sin theta cos phi, sigma z, or rather tau zy P by A sin theta sin phi. Now in the 2-dimensional case, the theta just represented the angle of inclination between the region of our interest and a normal to that to a specific point. So it just described the angle of inclination of our region of interest. We saw that the inclination of the area or the inclination of the loading direction both means the same, because we can rotate the frames of reference in such a way that the area is fixed but the loading direction is inclined, or we can also rotate it in such a way that the loading direction is longitudinal or along a definite frame of reference, but the area is inclined. So both these are equivalent. So in 2-dimensional case, we consider a situation, or we consider a system where the loading direction was along the longitudinal axis and thus the area was inclined. In 3-dimensional case, we plotted or we considered a system where the region of our interest was completely horizontal and therefore the loading direction was inclined. Now theta is the angle between, in 3 dimension, the theta is the angle between the loading direction and the normal to our region of interest, and phi is the angle between the plane that comprises of the loading direction and the normal to the x axis. So by having these 2 set of angular dimensions, that is theta and phi, having 2 sets of angular dimension theta and phi, one can describe the mechanical condition experienced by any plane and any direction in a 3-dimensional setup. So when you have a 3-dimensional system which is experiencing a uni-axial tensile loading, the mechanical condition that is imposed on any plane and any direction can be described by these thetas and phis. Now you can substitute those values and you can talk about any plane and any point in the plane, meaning any direction. So when you talk about a direction, there is a point, this direction comprises of several points, several elements, and you can then quantify the mechanical condition experienced by these elements. So what we have so far seen is, we have seen that under uniaxial loading or uniaxial tensile loading, a two-dimensional system, in a two-dimensional system, a region of our interest experiences a mechanical condition that is defined by or described by two components of stresses. In three-dimensional system, we have three components of stresses describing the mechanical condition experienced by our region of interest. Now, we should note that in three-dimensional case, this is a normal stress because this is along the direction that is perpendicular to our region of interest, and these two are shear stresses as they act along the surface of our region of interest. So the normal stress is acting perpendicular to the region of interest, and the shear stress is acting along the region of interest. So that is the reason why these two we have two subscripts for the shear stress and one subscript for the normal stress. So normal stress, the one subscript, it denotes the direction of the direction along which the normal stress is acting. That is, for this frame of reference, it is the z-axis. In case of shear stress, we have two subscripts. The first one representing the plane along which the shear stress is acting, and the second one represents the direction along which the shear stress is acting. So using these thetas and phi's, using these angular dimensions, one can then describe the mechanical condition experienced by any plane in a three-dimensional system under uniaxial loading. Now, at the end of the last lecture, we considered a triaxial loading in a three-dimensional system. So we began by considering a simple setup for three dimension, which is a rod, and this rod is experiencing a triaxial tensile loading along all the three directions. So it is experiencing tensile loading along the z direction, it is experiencing tensile loading along the y direction, so this is z, this is y, and it is also experiencing tensile loading along the x direction. So in this case, instead of talking about a region of our interest, we just chose rather a smaller simple element, a point or a simple element within this overall three-dimensional system, and we wanted to see what are the components that we need in order to describe the mechanical condition experienced by this simple element. So we want to see there is a point in our desired plane, and we want to know how one can describe what are the components that we need in order to describe the mechanical condition experienced by that point when the three-dimensional system is experiencing a triaxial tensile loading. For that, what we did was, in the previous lecture, we constructed this point as, or this element as, a cube. This cube, it subscribed to the frame of reference that we already considered, meaning this cube, which is the element in the three-dimensional setup that we have considered. So this is the cube, or this is the element of the three-dimensional setup, and we have drawn it in this manner, and this also follows the same frame of reference. So x, y and z. Now we want to see what are the components of stresses that are needed in order to describe the mechanical condition experienced by this specific element or a specific point within the three-dimensional setup under triaxial loading. So when we saw there is only uniaxial loading, we saw that it needs three components. So supposing there is a uniaxial loading, we saw that we need three components, one along the z-axis, that is the normal component of stress or the normal stress, and two on the z plane. So that would be two shear stress, one along the z-axis and two on the z plane. So that would be two components of shear stress and one normal stress, so three components of stresses. So for one uniaxial loading, we need these three components of stresses. So this would be tau zy and tau zx. So one under uniaxial loading, we needed three components of stresses to describe the mechanical condition. Now what we have is a triaxial loading. So therefore we can extrapolate it and we can say, so now we have triaxial loading. So the similar conditions will be experienced in this direction, one normal stress and two shear stress, and also along this direction, one normal stress and 2 shear stress. If you want to write the subscript, this would be sigma y and tau tau yz and tau yx. So this would be sigma x and tau xz and tau xz and xy. So we can write this notation by considering with reference to this frame and with reference to this coordinate system, and you can just try to write it on your own and see if we are able to, or if we are able to get to these components. So ultimately in the previous lecture we saw that when you have a triaxial loading, for each axis of loading you need 3 components, ultimately ending up with 9 components. So if you write it down, for the tensile loading or along the z axis you need 3 components, that is sigma z, tau zx and tau zy. We have for the tensile loading along x axis we have sigma x, this is the normal stresses, and the corresponding shear stresses, that is xy and tau xz. And similarly for the tensile loading along the y axis we have tau yx and tau yz. So we saw that we needed 9 components of stresses to describe the mechanical condition experienced by a simple element, a single small element or a point in a 3-dimensional setup experiencing triaxial loading. So the keywords here are 3-dimensional setup, a simple element or a point experiencing triaxial loading. So only when these kind of 3 keywords are satisfied, only when these 3 criterions are satisfied, you need 9 components. Now it is important to note that there are 3 normal stresses. So these 3 are the normal stresses. Let me be fancy. So these 6 make the shear components of the stresses. So uniaxial loading, you had 1 component of normal stress and 2 components of shear stress. In triaxial loading, for 3-dimensional case, at a point you need 3 normal stresses and 6 shear stresses. Now we wanted to see if there are any relation between these components of stresses, so that we can reduce the number of components that are required to describe the mechanical condition at a point when the 3-dimensional system is experiencing triaxial loading. So we want to see if there are any dependencies between these components, so that we can reduce the number of components and express only in terms of the independent component. So let us look into it. In order to see that, let us take a detour. Let us first understand how these shear stresses are experienced, what are the convention used for the shear stresses, and then try to see try to relate or try to understand if using that convention can we reduce this number of components. So what you want to do is reduce this number of components and just express it in terms of independent components. For that, let us understand how we have expressed this shear stress and study its convention and see if using that we are able to understand, or if we are able to reduce the 9 components that are required to describe the condition or to describe the mechanical condition experienced by a point in a 3-dimensional setup under triaxial loading. So we have seen that often whenever we have talked about the shear stress, the way we expressed it is this manner. So it comprised of 2 components. So at least for the sake of our discussion, since we are talking about a random shear stress, let us talk in terms of x and y. So whenever we talked about a shear component, particularly in 3 dimension, we ensured that there was 2 subscript for each shear component. The first subscript represented the plane, the second one represented the direction. Now the conventional way, or a rather easy way of representing the shear stresses, is by using what is called as a shear square, or rather a stress square. The stress square is a graphical way of representing the shear stresses. So what we mean by stress squares is just a random, or it's a regular square. I mean, of course all squares are regular, but it's just a square. So what you have is, in this square you will be representing your shear stresses, and the way you would be doing is, you would consider each of these sides of the square as a plane. So if you have a frame of reference, something like this, passing through the square. So this would be your x-axis and this would be your y-axis. Now this side here, which can be defined based on this frame of reference as y plane, because when you define it or when you express it in terms of this frame of reference, the y value would remain constant and the x value would change. That means this side in the red can be treated as the y plane. So that means the shear stress in this along this plane or along this side would be expressed in this way. Again, since this is a y plane, the shear stress acting along this plane would have the first subscript as y. And now if the shear stress is acting along, and since the shear stress is acting along the z direction, it is expressed in this manner. So what we are doing is we are trying to express or graphically denote the shear stress in terms of the plane it is acting and in terms of the direction it is acting using a simple square. So when you have a term that is tau yx, it means the shear stress is acting in this direction. Generally shear stress is represented by one headed arrow, I guess. So it would be, this is the conventional representation for it. I don't know why it is this type of a representation is chosen. Maybe someone interested can find it out, but it is represented by this partial arrowed sign. So in this square, the tau yx is represented by this. The stress acting along this direction is represented by tau yz, because it is acting along the y plane in the in the x direction. Now here if you talk about this plane, so let me highlight it in blue. So when you talk about this plane or this side here, like how we arrived at or how we refer to this as y plane, we can refer to this in the similar manner as x plane. So if there is a stress that is acting along this direction, then the way we would represent it is, we would consider it since it is acting along a plane, it would be a shear stress, therefore it is tau, and it is acting along the z plane, so the first subscript will be z, or rather it is acting along x plane, pardon me, and therefore the first subscript will be x, and since it is acting along the y direction, the second subscript will be y. So what the in this stress square, what we have done is we have just taken one side to be a plane, and we have shown how one could represent the stress acting along the plane in a particular direction. So that is all we have done. So similarly, when you talk about the stress in this direction, then you would end up with, since it is also acting on the y plane and along the x direction, you would end up with similar expression as above. And similarly, when you talk about stress acting along this plane in this direction, you would express it in terms of this. So far all we have done is we have just using this stress square, we have just represented the values of, or we just represented the shear stress using two different subscripts. So one can get acquainted with the subscripts using the shear stress. That is one aspect or one reason for using or plotting the shear stresses in a stress square. So when you plot the shear stress in a stress square, one can get used to having two subscripts for one stress component, and that is the and by that we have seen that the first the first subscript represents the plane and the second subscript represents the direction. Now the other reason why one would consider a stress square is that one can talk about, or we can talk about, the stability of the square depending on the inequalities between these two stresses. So we have four stresses acting on the square. Supposing if there are some inequalities, we can talk about what would happen in terms of the square. What I mean by that is, supposing this stress that is here, let's just talk about in terms of these two stresses. Supposing tau yx becomes greater than tau xy. So if this stress is greater than this stress, then what would happen is this square would start to rotate. Again, when this stress is greater than this one, tau yx is greater than tau xy, then this square would start to rotate. This would be in the clockwise direction, and this would disturb the rotational stability stability of the square. So when there is an inequality between these two stresses, then the rotational stability is disturbed, and depending on which stress is greater, there will be a rotation along a particular direction. Supposing if tau xy becomes greater than tau yx, then there will also be a rotation, but in the anti-clockwise. So what happens is that when you have an inequality between these two, there will be a disturbance in the rotational stability and the square starts to rotate. Supposing if the square represents a section or a small element which represents a point. In that case, since a point, which is again a theoretical conception, since a point cannot rotate, since a point is just an element of a system, it means that at a point or in an element that we considered, or a point that is being represented by a cube element, for our understanding, again the point is again a theoretical conception, the cube element that we are building is for our understanding. When you consider this is a point in a system, that means that that point should have a rotational stability. In that case, when you want to have a rotational stability, tau yx should be equal to tau xy. Remember, we are talking about a point, again a theoretical conception, and we have drawn a cube out of this point for our understanding that it is not physical. So when you have such a point, we need to ensure that, because whenever you have a point that is rotating, it is no longer a point, it is something a movable one. A point is for us, or this conception is for us to pinpoint a particular space in a system that is constant or that is fixed. And when you have a point that is rotating, it is no longer fixed. So when you want to talk about a point, it needs to ensure that we need to ensure that there is a rotational stability to that point. And one way of ensuring that rotational stability is when these two components of shear stresses are equal, and when so the rotational stability corresponds to this equality. Now again, in addition to this rotational equality, there is also a need for the to ensure the horizontal stability. So in addition to the rotational stability, there is a need to ensure this horizontal stability so that the net force acting on the square is 0. So in order to ensure this horizontal stability, so what I mean by that is, in case of horizontal stability, these two stresses should also be equal. These two stresses should also be equal, even though they are given by the same notation. We will see why we have, if you have a closer look, we have given a specific direction to the stresses here. We did not choose a random direction, we have given a specific direction. If you have a doubt on why we have chosen that specific direction, it will become clear in few minutes. But under this representation, these two stresses are also equal. So let me again use say blue. So these two stresses are also equal, meaning they give us a horizontal stability. So what we have is, we have ensured a rotational stability of a small point using the stress square, and we also ensured that we are shown that under definite condition the rotational stability is ensured, under definite condition the horizontal stability is ensured. Since we are talking about a fixed point, if we are talking about a fixed point, then we can use these conditions to describe the stresses at that fixed point. Now let's get back to this question we had, which is why one should consider only this direction, since both these axes, both the entire axis, this entire axis, since it represents the y-axis, why in this case we chose this direction alone? Why not choose this direction? Why not choose this direction? Why did we choose? Because these are the axes. So even this falls under x-axis, and this falls under x-axis, this falls under y-axis, and this falls under y-axis. Why did we choose here specifically this particular direction? So that is another thing that we want to answer. Now, to answer that, we need to understand the conventions used for shear stresses. So in the previous lecture, when we talked about tensile stress, we saw that when the tensile stress is, or when the stress, or when we talked about tensile stress, we saw that when the with respect to the material that we are studying, when the load acting is tensile, then by convention this stress is positive, and when the load acting is compressive, we saw that this stress is negative. We saw the reason for this convention is because only when we use this convention we will be able to arrive at a material property that is common for both compression loading and tensile loading. So this would be compressive stress. So only when we have a definite conventions like this, we will be able to get we will be able to arrive at an equivalent material condition for both tensile stress and the compressive stress. So we need to have a similar convention. We need to have a similar convention for the shear stress. All these previous conventions were for normal stresses when you talk about components of stress. Now what we need to have is a similar convention for shear stresses. So the way the shear stress convention is defined is again by using a stress square, but now we have to consider the different quadrants. In order to understand the convention of the shear stresses, we need to consider the shear stress square but the different quadrants. Now let me use red to define the axis because it is important. This is the the y axis, and this is rather the x axis. So this is negative y axis, let us assume, and this is positive y axis. Let me be as legible as possible. So this is positive x axis and this is negative x axis. So instead of just considering x and y axis, now we have defined positive region, negative region with reference to the center point of the stress square that we have considered. So with reference to that center point of the stress square, considering that to be an origin, we have now defined positive x axis, negative x axis, positive y axis, negative y axis. Now by convention, your shear stress is positive when it is along or it is in the positive plane and acting along the positive direction. So that means only when your shear stress is acting on the positive plane, that is in this region. So this plane is on the positive side of the x axis. When you talk about the x axis, this plane is on the positive side of the x axis. So with respect to the x axis, this plane is on the positive side and this plane is on the negative side. So if I use blue, so blue will be on the negative side of the x axis. So this is negative side of x axis and this would be in the positive side of x axis. So we now have differentiated one plane from another, even though they are all along the even though both of them are y plane, we have differentiated depending on their position. So one is a positive y plane and the other is a negative y plane. Now a shear stress is positive only when it is acting along the positive y axis in the direction of positive x axis. So it should act along positive y axis in the direction of positive x axis. So the positive shear strain in this case would be this one. So this would be the positive shear strain because it is acting on the positive y axis along the positive x direction. So this would be a positive shear strain expressed by yx. So this would be a positive shear strain. So what would happen, or what would be the convention of the shear strain that is acting along positive y plane but along the negative x axis? Meaning if I have I'll use this. If I have a stress that is acting along the positive y plane but that is acting on the positive y plane but along the negative x axis. So what is the sign for this kind of stress? Again, when we write it in this manner because it is acting along y plane and in the x direction, but now it is acting along the negative x direction. So by convention, this would be a negative shear stress. So what we have is, we can have a positive shear stress when the plane on which the actual stress is acting is positive in terms of this in the stress square, and it is also acting along the direction which is positive. Only in that case you would have a positive shear stress. When your plane is positive and the direction in which along which the stress is acting is negative, then you would have a negative shear stress. So let us consider a case wherein the plane is negative and also the direction is negative. So under such a case wherein the plane is negative and the direction is negative, so such cases would be something like this. So this plane here is with respect to the y-axis here, or if you come with respect to the quadrants here, as you can see, this plane lies in the y direction, or it's on the y quadrant. So when you have a plane that is on the it's on the negative quadrant. So this plane here, if you talk about in terms of the x-axis, it lies along the y or the negative quadrant. We are talking in terms of the x-axis, it lies along the negative quadrant. And now when you can have two directions of shear stresses acting on this plane. So one could be this direction, the other could be this direction. At least using by virtue of my colors that I use, you could have now guessed which one is positive or which one is negative, but let me try to explain. So what we now have is a shear stress acting along a plane that is on the negative side of the x-axis, a plane that is on the negative side of the x-axis, so a negative plane. And there are two possibilities on which the stress could act. One is along the negative y direction and one is along the positive y direction. The stress in this case, when the plane itself is negative, the stress in this case can be positive when the plane and the direction are both negative. So here the plane is already negative, it is acting along the negative y plane or negative x plane rather, and now only when the stress acts along the negative y direction, the shear stress is positive. So this stress is acting along the negative x plane. Again, with respect to the frame of reference that we have considered, it is acting along the negative x plane, or acting on the negative x plane along the negative y direction. So that means that this is a positive shear stress. However, if you consider this one, the shear stress represented by this arrow here, or half-headed arrow here. So this is, even though it is acting along the negative x plane, it is acting on, even though it is acting on the negative x plane, it is acting along the positive y direction. So that means this is also a negative stress, or this is a negative shear stress. So by convention, what we have is, when your plane and direction are of same sign, then your shear stress is positive. So if you want to write it in simpler, just by using these notation, when you have same sign for your direction and plane. So when you have similar sign for your plane and direction, then your shear stress is positive. So this would mean this would also include negative x and negative y, and this would also include y plus x, and rather minus y minus x. So all these are by convention positive shear components of stresses. So by convention, when your direction and plane are of the same sign, then by convention the shear stresses are positive. On the other hand, when you have a combination of plane and direction, which is something like this, plus x minus y, or minus x plus y, tau minus y plus x, or plus y minus x. In cases like these, by convention, these are, let's use the same, so these are negative shear components of stress. So since the shear stress involves plane and direction, the convention is also rather convoluted. In the normal stress, it is just tensile, it is positive, and compressive, it is negative. But in case of shear stress, since it involves plane and direction, both these plane and direction should follow the same sign. Only then the shear stress will be positive. If one of these signs are different from another, then it follows or we call that as a negative shear strain. So this is the convention for the shear stresses. Now what we have seen so far is that we have seen that for an element, for a point, when you talk about a point, a fixed point, then in order to maintain the rotational stability of the point, tau xy should be equal to tau yx. And for the sake of this argument, we just confine ourselves to positive shear stresses. And of course, we need to again understand that we are talking about a single point, and this single point we have not defined or quantified the stresses acting on each. We have not quantified the components of each of the stresses. For that, we need theta and phi. This theta and phi depends on the plane that you have considered and the direction that you want to go. But so far what we just want to focus is just how many components do we need. That is all our focus is. So we have seen that when you consider a three-dimensional setup experiencing a triaxial loading, we need three components of stresses. We want to reduce it to independent components alone, and we saw that by virtue of the stress square, we saw that when you are talking about a fixed point, in order to maintain its rotational stability, this condition needs to be fulfilled. Now let us try to rewrite the components that we have already seen that are required to describe the mechanical condition experienced by a point in a three-dimensional setup when it experiencing a triaxial loading. So if you try to write that, it would be sigma z again for a frame of reference, something like this. Sigma z tau zx, sigma y tau yz and tau yx, sigma x tau xz and tau xy. Now these are the components that we saw are required to represent the mechanical condition experienced by a small point or an element in a three-dimensional setup experiencing a triaxial loading. Now let us try to use this criteria for rotational stability, considering that we are focusing on a point. Use this criteria for rotational stability and see if we can reduce the number of components that is required. So what we have here is, then using this criteria, then it would mean that these two are equal and these two are equal, and let me just find another color. Yeah, so these two are equal. So only when they are equal, you will be able to ensure the rotational stability of your point. The point by definition is a fixed one, so it should not rotate. So this should be ensured. So that means that, so ultimately we can, since these are equal, we can then express the number of independent components that are required, to define, or rather number of independent components that you need to define or describe the mechanical condition experienced by an element in a three-dimensional system experiencing triaxial loading. This is so important that I have to write these keywords. Triaxial loading, only when triaxial loading is experienced by the material, you would need these many components, and this is for a three-dimensional case. And again, let me repeat, we are not quantifying each of these components. We just want to know, or we just want to count how many components we need when you want to describe the mechanical condition experienced by a point in a three-dimensional system experiencing a triaxial loading. So since these are equal, then we can write the required number of components as, let me write it easier in a way that is easier for you to understand, tau x, tau y, tau z, sigma xy, sigma x, sigma y and sigma z, tau x, tau xy, tau yz and zx. So what we have done is, we have reduced the 9 components to 6 components by using or by considering a single point that is stable rotationally. By under such assumptions, we can say that the number of components, when you want to talk about a single point, then the number of components that is required to describe the mechanical condition of that point, which belongs to a three-dimensional system experiencing a triaxial loading, is we need 6 components, 3 normal stress components and 3 shear stress components. So these are the 6, again the key word is independent components. If one asks you about what are the maximum number of components that you need, then it would be to describe a mechanical condition experienced by a point in a 3-dimensional domain under tri-axial loading. If that is the question, what is the maximum number of components that you need, then the answer would be 9 components. But when the question is specific about what are the number of or how many independent components that you need under to describe the mechanical condition, tri-axial loading 3-dimension, you have to know this keyword, tri-axial loading 3 dimensions. So under this condition, then the answer is 6. You need 6 independent components. So what we have done so far is, we have in this discussion on components of stress, we have introduced the component of stress by considering a 2-dimensional system. We saw then in that case there will be a normal stress and the shear stress. In case of 3-dimension, we saw there will be 3 components of stress. Under uniaxial loading, we have 3 components of stress. 1 normal stress acting normal to the region of our interest, and 2 shear stresses acting along our region of interest. In case of triaxial loading, we saw that there are 9 components of stresses that are acting, 3 normal stresses and 6 shear stresses, 3 normal stresses acting perpendicular to our element, our point, and 6 shear stresses acting along our point if you consider it in terms of cube. And now, since we are talking about a fixed point, then we were able to ensure that these points are rotational stability, and by virtue of it, we were able to reduce the independent components, 9 components to 6 components, and ultimately, or we were able to reduce the dependent components, and ultimately we saw that for a 3-dimensional system experiencing triaxial loading, the number of components required to describe the mechanical condition at a point is 6 independent components, 3 normal and 3 shear. Now, there is also another way to ensure this equivalency, that is another way to ensure that these 2 shear stresses are equal, and that would involve that assumes that the dimension of the point is small and therefore the moment of force is small. So that being said, so when you have a point and the moment of force is small, you can write something like this for a 3-dimensional element. If you want to write the moment of force, rather something like this, the moment of force at a point is equal. You can and since we are considering a small dimension or a small element, and these are the dimensions of these elements that we are considering, and ultimately you will end up with the similar equality. So there are ways to arrive at this equality. So one we saw that is by using the rotational stability argument. The other is by ensuring that the moment of force is equal at a point, and therefore again you end up with the same equality, and this equality helps you reduce the number of components. So irrespective of how you arrive at this equality, what we now know is, when you have a 3-dimensional system experiencing triaxial loading, then to define the mechanical condition experienced by a point within that 3-dimensional system, you need 6 independent components, and you want to have a maximum number of components, then it is 9. So with this with this point, I would like to wind up with this lecture, and maybe in the next one we will try to build on it. We will try to make it more specific, and we will try to get into even more interesting things of graphically representing the state of stress. So what we have so far seen, when I talk about components that you need for a mechanical condition to describe the mechanical condition, component of stresses you need to describe a mechanical condition, this is one way of talking about the state of stress. So maybe we will try to introduce that in the next lecture, and try to build on this understanding, and try to represent all these in terms of our attempt to represent in terms of make a graphical representation of all these components of stresses. So please listen to this lecture at your own pace, and you can of course let me know if you have any questions, or if you have any if there are any inconsistencies with these arguments. So thanks for your time, and we will see ourselves in the next lecture.